Okay, now we're going to look at how to solve team challenge number 4. This is where a lot of people hit the wall because it was long. But you got to realize that this you have to be able to do on your own by the test, which is going to be on Tuesday the 24th. So let's start by going over the first part on page 1, which was just to describe the preparation of a buffer. We worked through this in class, but I'll go over it here. So our givens, for starters, 820 mils, which is 0.82 liters, of a 220 millimolar buffer, which is 0.22 molar. We have an acid-base pair which has a pKa of 5.17. We're at a pH of 5.5. And we have our salt at 66.6 grams per mole. And we have a 0.9 molar solution of HA. So, we also have distilled water. So this is what we have in the lab. This is what we're trying to do. Now we've got to figure out where to go. We're going to start with Henderson-Hasselbalch. We're going to start to figure out the ratio of A- to HA. So we have our pH of 5.5 equal to the pKa, 5.17, plus the log of A- over HA. Okay, that makes that value 0.33 is equal to the log of A- over HA. And when we take the anti-log, or 10 to the 0.33, we end up with a value of 2.138 as the ratio of A- to HA. Now, from the question, we know that the concentration of the buffer is 0.22 molar. And what that means is that the concentration in the form of A- plus the form of HA together make 0.22 molar. So what we have here now is our two equations, two unknowns. We're going to express one of these in terms of the other. So I will multiply both sides of this equation by HA and have it say 2.138 times HA is equal to A-, which I will then substitute in to this equation to solve for HA. So I will say 0.22 molar is equal to 2.138 times HA plus 1 times HA. And that can then solve for the concentration of HA to be equal to 0.22 molar over 3.138, which gives us a value, when you do the math, of 0.0701 molar. Now the sum of the two is 0.22 molar, so by subtraction I can get the concentration of A- at 0.1499 molar. Okay, so I have my two concentrations. Now I have to figure out how many grams I have to weigh out and how many mils of the weak acid I have to measure out. Let's start with the conjugate base, which is a salt in this case. I have 0.1499 moles per liter, but I'm only making 0.82 liters. Okay, so I need this many moles. I need 0.1229 moles. Okay. How many grams is that? I multiply by the number of grams per mole. And that gives me a value of 8.19 grams. So the first part of the question, the answer is 8.19 grams. For my weak acid, I have 0.0701 moles per liter times the 0.82 liters is equal to 0.0575 moles And for that, I need to divide that by the concentration of my stock solution, which is 0.9 moles per liter. So that will give me an answer in liters, which is 0.0639 liters, which is equal to 63.9 milliliters. So to make my buffer, I simply need to mix this many milliliters of my stock solution of acid with this many grams of salt and fill to 820 milliliters with water. Now just before we do the buffering capacity, I'll go over the bottom part of the page, which is a simple, what is the pH of a weak acid solution question. It said, what is the pH of the 0.9 molar bubonic acid used in part A? Well, the only given we have is that the pKa was equal to 5.17. So what we have to figure out here to do this simple question is just what is the Ka? Since a pKa is the negative log of a Ka, 10 to the negative 5.17 is going to be equal to Ka, which, as it turns out, is 6.76 times 10 to the minus 6. So then it's simply a question of saying, okay, Ka is equal to concentration of H plus times the concentration of A minus all over HA. If we do a little ice table, we simply say, okay, we started off with it's 0.9 molar HA. Let's call this 0 and this 0. Some amount, X, dissociated into H plus and A minus, and this left us with this left us with a little less HA and a little more H plus and A minus. So at equilibrium, we have 0.9 minus X, X, and X. If we assume the 5% rule, we can go right ahead and say that the Ka is equal to X times X over 0.9, because we're assuming that this, now X is very small compared to 0.9. Therefore, the Ka times 0.9 is equal to X squared. Ka times 0.9 is equal to 6.08 times 10 to the minus 6. Okay, which makes X, if I take the square root of that, equal to 0.00247. Now X is my H plus concentration. Take the negative log of that, I get a pH of 2.6. Okay, let's move on to the buffering capacity questions on the other side of the page. I'm going to start with part B because it's like the one that we worked through in class today. In this case, it asks, if you take 50 mils, so not the whole volume, but only 50 mils in a little beaker, okay, how much 1 molar NaOH do we have to add to increase the pH by 1 unit? So if we're going to increase the pH by 1 unit, we're going to go from the 5.5 we were at before to 6.5. So basically we have to start by solving for the Henderson-Hasselbalch equation, the ratios and the concentrations again. We're going to go to pH 6.5 is equal to our pKa, it's still the same at 5.17, plus the log of A minus over HA. This gives us 1.33 equal to the log of A minus over HA, and a ratio of 21.38. Note we're well above the pKa now over a pH unit, so this number is greater than 10. All right, using the same approach that we used last time, we can solve for concentration with 2 equations and 2 unknowns. And we get concentrations of HA equal to 0.0098 and of A minus at 0.2102 molar. Note that this is, the solution is predominantly deprotonated at this pH. Okay, now what we need to know, how many moles of each of these species do we have in our 50 ml volume? These were our old concentrations, original, okay, and these are our new concentrations, okay? So, let's start with the new concentrations. We have concentration of HA of 0.0098 moles per liter, but we only have 0.05 liters. It's 50 ml aliquot, which means that we only have 0.00049. You really got to watch your zeros in these questions. Moles of HA. With the A minus, we have 0.2102 moles per liter times 0.05 liters gives us 0.0105 moles of A minus. That's the new, okay? Now we use our original, what the buffer was like when we started. We had a concentration of HA from up there of 0.0701 moles per liter times 0.05 liters equaling 0.0035505 moles. And we have an A minus concentration that we started with of 0.1499 moles per liter times 0.05 liters means we started with 0.0079495 moles of A minus. Now what we have to do is to figure out what the difference is between our final moles of A minus and our original moles, or 0.0105 minus 0.007495. That gives us a difference of 0.00, I think it's 3005, something like that, moles. You should get the same difference, but in the opposite sign for the HA. Final moles of HA minus original moles of HA. And so this is equivalent to 3.00 mils of 1 molar NaOH. I took the number of moles I had divided by 1 mole per liter solution. So 0.003 liters is 3 milliliters. Okay, that was the one that was similar to what we did in class. The other part, part A, is a little bit trickier. We're going to start by using the information that we found here. So I'm going to get rid of the other stuff I just did. This is what we had in solution to start. Still a 50 milliliter aliquot. And this is how many moles of A minus and of HA that we started with. Now in this question, it tells us that we have added 8 mils of 0.5 molar HCl. Alright, what that means is we have added 0.008 liters at 0.5 moles per liter, which is 0.004 moles of H plus into that solution. So really the easiest way to think of this, I think, is doing a little ice table where we have our HA, our H plus, and our A minus. And to start with HA, we take our number from over here, 0.003505. We're not going to talk about H plus. A minus, 0.007495. These are both in moles. we add is 0.004 moles of H+. So I'm going to add that here. Now when I add H+, it combines with A-, so A- disappears and becomes HA. So the HA pool is going to increase by 0.004 moles, and the A- pool is going to decrease by 0.004 moles. Okay, because we're combining with it. So we do our sums, and we end up with 0.003, what is that, 3495 moles of A-, and we end up with 0.007505 moles of HA. Now, at this point, there's two things you can do. You can calculate the new concentration. The volume would be 58 mils. But it turns out because we're going to put them in Henderson-Hasselbalch and they will be a ratio, the volumes will cancel out. So generally speaking, I don't bother to do that. I simply go into the Henderson-Hasselbalch and say, okay, the pH is equal to the pKa plus the log of A- over HA. This pH is going to be equal to 5.17, that's our pKa, plus the log of A-, 0.003495 over 0.007505. Okay? That gives us a value of 4.84 when you calculate it out. So you can expect on the first midterm for there to be buffering capacity questions of at least those two different types, plus a make a buffer question.